Okay, everyone, it's my pleasure to introduce Anna Slobodova from Intel. She is well known for the work that she's done on hardware verification, first in Centaur and now in Intel. This is, I think, one of the real flagship projects, and I consider it one of the things that I'm most proud of that this verification community has produced. So it's a real industrial piece of hardware that's been subject to intense formal verification. So Anna is the leader in the project, and she'll be telling us about the work that she's been doing at Intel.
Thank you very much, Shankar. So I am at Intel, like Alistair, but we are in different divisions. While Alistair is in Intel Labs, I am in Advanced Architecture Group. And so we are associated directly with the Microprocessor Design Group. So I will a little bit talk first about differences between architecture and microarchitecture and how we do the modeling. So while Alistair was on an ISA model, we are working with microarchitecture model. I will tell a little bit what I believe are requirements for successful hardware verification and what was our approach, specific proofs and tools that we have been using, and how we model things, and then summary and conclusion. So this is a work of my group. Saul, Vivek, Marcin, and Mihir, and Kang are in my team, and Warren was consultant to our team. So, architecture. So you heard from Alistair about modeling of instruction set architecture, or ISA, and everybody knows different examples, like besides x86, there is ARM or RISC-V. It is public document. It's written in English and complemented with different tables and pseudocode. And it describes formats, operational semantics, how every instruction changes the state, and basically all information that software developer needs in order to write compilers or program in x86. So it's different architecture have different rules. For Intel, they always keep the legacy and expanding architecture, but the code that ran on Intel machine 20 years ago is supposed also run now, what brings a lot of complications. It's as I said, mostly relevant for software engineers and verification engineers, or simulators are written with respect to ISA. So with microarchitecture, you are getting a little bit deeper. So every new product might have not either different technology for the processing, but mostly it has also different microarchitecture. So it needs to be compliant with ISA, but it is like some people call it refinement, where it has much more details about how this product is implemented. So if you look at examples of specific products at AMD, there are Ryzen's and Apple A, Apple B, Apple M, and Intel has Core i5, 7, etc. Unlike ISA, microarchitecture is proprietary. It's often considered top secret. It's also written in English and has some pseudocode and block and timing diagrams. So it describes basically all the details that are necessary for RTL designers to implement it. What is the hierarchy? what is the latency latency of the instructions, how the caches are organized, what are the sizes of caches. It depends on what throughput we want to reach, and also there is description of how the power is managed. Microarchitecture specification is relevant for hardware designers to finish the project, and also for verification engineers. The machine should still implement ISA, so it's not that interesting for software engineers. You can look at it that while ISA says what is implemented in machine, the microarchitecture describes how is it exactly implemented. So it has different objectives. The modeling of architecture and microarchitecture. So architecture specification, as I said, is used in software and hardware verification. And usually what you want is to use it to analyze the completeness and consistency of ISA. While microarchitecture specification is used for either hardware verification or microcode verification. I believe that we need to link both the microarchitecture specification and ISA, and so it's usually good if it is in the same formalism. In this talk, I will talk only about microarchitecture specification, and Warren will talk later, I think on Thursday, about architecture in the same formalism. So very often when I read some papers in conferences, etc., they show this simple picture of microprocessor behavior. It does fetch and decode of instruction, execute instruction, and then writes it back in registers in our memory, etc. But in fact, it's much more complicated. So in order to design high-performance microprocessor, you have many fetch and decode units. And for x86, it's actually much more complex than for many other ISAs, because the instruction length is not fixed. So when you are trying to decode, fetch and decode a dozen or more instructions where you don't even know where instruction starts and ends, it can be tricky. And then, so you do a lot of speculation, a lot of parallel decoding, and then also the execution clusters want to execute in parallel, so we have many of those. Each cluster has many ALUs, and in each ALU you have a lot of units that implement some specific class of instructions. And in between you have out of order, where you do analysis of dependencies of instructions, so you know that you can change the order, you can send them to different execution clusters. Those clusters also are not identical. They can be configured in different way. And then there is speculation about data, speculation about control, or ALUs even are deep pipelined. That means you are sending the new instruction before the previous instructions finished. How you schedule them, that's also very complicated, because you try to schedule dependent instructions close by, either in same execution cluster or even same ALU, so you can forward the result as fast as possible. And because this design is massive, you also have basically copies of different elements of states all around the chip, so they can get some architectural registers, get access as fast as possible. And if you take into account the speculation, and that sometimes you need to undo your work and keep still track of these copies of the state elements that it gets really, really complicated. So when I see a paper that says they did end-to-end verification of some microprocessor, I'm wondering what microprocessor it was, because you definitely cannot even successfully build the formal model of the whole thing. And so what can we do then? Well, maybe we start bottom up, start to do what we can do, and then put pieces together. For that, of course, you need a rigorous way to decompose the problems and then compose them back together. So in this talk, I will focus on verification of execution cluster. So as you see, this is just very small part of the overall design. And within this, we have different ALUs that can execute integer, floating point, crypto, and other instructions. So our goal was, when we joined Intel, was to be able to verify a complete set of micro operations that execute in execution cluster. And we were trying to do it with minimum assumptions on environment. For instance, we don't assume that instruction is existing in the machine in isolation. So we need to take into account all the instructions in flight, and there are dozens of them in one ALU at any moment. There is very strong power management that is turning off individual flops and latches whenever data do not need to flow through it. That brings, again, other problems with security, that you don't want any stale data to be left in these flops when they are turned back on, etc. So all this is part also of our verification. Mm-hmm.
Can you go back to the previous slide?
Yeah.
So, what is the challenge in modularizing all the verification, something big?
The challenges in, so, first of all, we cannot just build one finite state machine from everything. It's just too big. That's one thing. So we need basically to do specification and verification from the smaller blocks and building it up to bigger blocks. In our case also, x86 instructions, when it enters the machine and it's decoded, it's translated in a sequence of micro-operations. Now, we start with some very abstract micro-operations that are still, some of them might be just almost like instruction. They might, for instance, it might implement floating point division. But there are also other instructions that help to implement the full, let us say, AVX instruction. So those are further translated into even smaller micro-operations, and they can be fused again. So the life of instructions is really complex. If you want to capture that, that's another layer of things. And that is something that might be different from project to project. So you will need to update it. That's another challenge. Just the size of, we have close to 4,000 micro-operations just to write specification for each of them and track whether the proofs has been done. And of course, once it is done, you need to be able to rerun it quickly, because our designers are waiting for response every day. They are changing design, etc. So that's another. Yeah.
Can I ask about that? So how stable are those micro-operations?
How stable they are? Relative stable for the project. And in some cases, So it's all depends. So usually what happens is that time to time Intel comes with completely new microarchitecture. And in some cases, they might even try to modify ISA, either simplify it or they are extending it all the time. But once the project started, there is some phase when architects come and they do all the modification and everything, but then it is supposed to be frozen at this point. They say like, okay, this is the set of microoperation, etc. So, and the next project, it depends. The next project probably will be very similar. They might remove some, add some, but then few years later, they might again come from scratch, something new. So that's so our goal is basically to make sure that every microoperation executes correctly, and that would give us more confidence in the hardware implementation. But at the same time, we didn't go just for hard instructions or corner cases. We wanted to cover the whole set of microoperations. And the reason was because we wanted to build complete microarchitecture specification that can be used for microcode verification. That was the secondary goal. So as I mentioned, the scope is arithmetic and logical units, but they are much more complicated than what you find in some textbooks where it says like, okay, this is add or subtract or something. Like one ARU might be implementing all floating point instructions. Another can be crypto instructions, etc. So they have each ARU has within different units, and those units might process instructions with different latency, and they write back to the same bus. And so what does it mean that a microoperation executes correctly? So we basically did 3 steps. First was if the ARU gets a legal opcode and the operands satisfy the constraints that come with that microoperation and control signals too, then it will execute correctly, starting from a good state. And what good state is, we have to find invariant of good state, prove that it's inductive invariant, and then a reset sequence will get it to that state. So we use ACR2 with many built-in automation tools. Yes?
Does that specification also take into account speculation? Like if you execute something and then it needs to be rolled back or something?
It depends. So in ARUs, it will be very low level that there will be control signals that might say this ARU at some point, like the result cannot write back. So then that needs to be taken into account. So, but by the time instructions come to execution, we also do not know even whether it's in machine mode or user mode, how to protect the data. So everything needs to be specified in different ways. So it's a much lower level. Yes?
Micro specification, is that written in ACL2?
Yes.
It's handwritten.
Yes. So now why ACR2? So I believe that if you want to do formal verification of hardware, then you need, you expect some features of the language. It should have formal semantics so we can reason about it. It needs to have large-scale tool support with the good execution. So the formalist needs to be executable because we need to validate our specifications, and we need to be able to run models of design. So both actually, the design and specification will be translated into ACR2. And we need fast execution of the specification for validation purposes. What we do, for instance, we might take the specification and run assembly program that uses specific instruction and run that on previous Intel machines to compare exceptions and things like that. And also our formal model of design should be evaluated fast. One of the really important things is also that we work on design that is changing every day by designers. Specification might be changing by verification engineers. Microcoders might change their part. And so we need to have a way to build model from modified hardware very quickly and rerun our proofs or get back to the point where we left it yesterday. So we take system Verilog, and I mention later what we do with that. But this translation cannot take days. It needs to be done in minutes for us to be efficient. And the other thing, what maybe it's not must, but we found very useful, was that the formalism that allows extensibility worked very well, because we were able to write tools in ACL2 and prove them correct, and then basically turn them into cross processors that were then part of the logic and theorem prover. Since we want to build bottom up the proofs, we need also a way to decompose programs and compose back results. So our choice was ACR2 for many reasons that I will tell you. So for those that don't know, it's the language. It's also first order logic. As a language, it's a subset of Lisp. So it has compilers and everything you need. And it's also proof system that supports proof checkers, etc. So as a language, it can be used for scripting and writing tools, and also for proving theorems. It has been used in academia and also in different companies like AMD, ARM, Kestrel, Centaur, and now Intel. And it has been used for both for software and hardware verification. So that this versatility is also something that is important to us. So it's open source, so it's free. And it was expressive enough, believe it or not, those that work with high-level logic, that it was good enough for our work. It's executable. So that was important for validation of our specs. It's very efficient. Very efficient not just in execution, but also we end up to have thousands of files that need to be recertified. And ACL2 is very good in creating, kind of figuring out dependency and certifying in the order that can be highly parallelizable and just work over NetBatch and bring everything to correct state very quickly. Another thing that is important for us, that it allows separation of the public information and proprietary information. So if you look here, so the ACR2 has kind of, this is the base, the system that comes, and on top of this system, we have public libraries that have, for instance, BDD package, AIG package, symbolic simulator, different rewriters, and also, so our team built a lot of tools. For instance, one is that translates system Verilog into finite state machine, and that's in public library. But then we have specification, microarchitecture, and or information that comes from microoperation database. And then on top of that, there are proof scripts that can be, again, made private or public, dependent on how you feel about it. But since we use private libraries for specification, then that doesn't make sense to release the proofs. You can also connect other tools to it, either through foreign function interface. So from these three that I mentioned, we use SAT servers, any off-the-shelf SAT server that has a standard interface can be plugged, and then we check the certificate from SAT server within ACR2.
Question? I would have a question.
Yeah.
So you say on the right-hand side you have private ISA specs. How closely are they related to the ISA specs that we heard of in the previous talk?
So they are not related at all to ASL specs, and the reason there is, first of all, Alistair and I came to Intel at the same time, so there wasn't any ASL spec. But there is actually public x86 ACR2 spec that Ward will talk about, and it is related. So we are connecting microoperation specification to instruction set architecture. As I said, in many cases, instruction is translated to one or two microoperation, in which case this microoperation might have extra flags and a little bit different behavior, but it uses the specs of for data, for instance, result and exceptions the same as is in ISA, but then modifies response of the machine to, let us say, exception and interrupts.
I have a question.
Yeah?
Is it of a similar scale? Are you talking about hundreds of thousands of lines of ISA spec?
How many? I actually didn't look how many thousands. It is bigger. Microarchitecture has more operations than ISA. But since we were starting build bottom up, for instance, with respect to access to memory, we had only microoperations for computation of address and the recognition of different exceptions like paging and segmentation fault and canonicity, etc. But we don't deal with some of the features that are in ISA because they are just high-level features. They translate at some point. So as we will expand our microarchitecture model, then hopefully they all connect. But we are not that far. So ACR2 is actually very well documented. It has web-based and command-based documentation, both the core ACR2 and the libraries. Libraries, it all depends on who is the author. Some people document it better, some people less. As I mentioned, it's extensible, so we have a lot of point tools that were developed and then verified within ACR2, and then they are used for different verification tasks. And for us, as a group who is based in Austin, we were lucky that we are where UT is, where ACR2 has been developed, and so there were students that we could hire, and they were already trained for using ACR2. So now, a little bit about tools that we built within ACR2. One of the most important is translation from system Verilog. That is pretty complicated, and especially it's very hard. People often ask me how many lines of code we translate, and that's really hard to say because we have, for instance, some modules that are instantiated many times with completely different parameters. And so you can even parameterize over data types, what is a pain for us. But so it's really number of lines of code is not really measured to how big this is. But whenever we work on some ALU or the whole execution cluster, we want to be able to come in the morning, update design, update whatever proofs who did, and quickly build the model. And so building the model consists of, first we flatten the hierarchy and process system Verilog, that means parsing, elaboration, normalization, etc. And then that is actually translated, this netlist is in formal language that is called SVEX. It is part of public libraries in ACL2, also designed in our group several years, like 10 years ago or more. And then from this netlist, we built finite state machine, and in order to do proofs, usually we do some unrolling of the several steps of finite state machine. So from basically here, since this is written in, SVEX has formal semantics, down here, all these transformations have been proven correct within ACL2. So our main engine that we use is calling GL or FGL now. It's the new generation of that. So how is it used and what it is? So imagine that you want to prove that some microoperation executes correctly in ALU. So first we write, specification in ACL2, and then we build the model, and let us say that the operation has latency of 7 cycles. So we unroll the circuit basically with symbolic stimulus for the number of cycles, what is the latency, and express this equivalence as basically as a Boolean formula that can be then, you can apply or known our tools in our Boolean solving toolbox. We have, you can apply combinational logic simplification, equivalence sweeping, SAT solving, AIG simplification, you name it. But on top of that, we can use also rewriting. The rules are, of course, proven within ACL2, and that simplifies a lot of things. This allows us also to work on higher abstraction level and rewrite specs from one form to another that would help the automatic tool to verify it. So at the end, you either get the proof in ACL2 and the theorem, or you get counterexample, and that counterexample, again, we have a lot of debugging tools within ACL2 that are targeting the formal verification engineers. But we have also, like, when we find out that definitely the problem wasn't with our stimulus, it wasn't with our specification, if it is a bug, then we can translate it in actually SVA assertions that can be sent to Jasper Gort or anything else. It's like very simple, concrete example, but it gives designers the same environment that they are used to. So they rerun this counterexample with Jasper Gort or Verdi and open their interfaces that connect waveforms to RTL and can trace all the signals as they please. So.
Question?
Yes.
So I'm curious. So generally, you're reasoning at the system Verilog level.
A finite state machine level. So we translate everything in finite state machines, and then we work with that.
I was wondering if you could compare that to other approaches. Like I there's some people trying to reason about sort of blue spec, and there's also people trying to reason about Verilog itself. So is there like a...
So the problem is that system Verilog, if you take complete language, I don't know how they reason. You can probably do equivalence of two Verilogs. That's a possibility. But our specs are very high level, so they are not system Verilog. Like if you try to prove square root, you don't have another square root system Verilog to compare.
No, I know your specs aren't within...
Yeah.
With your model of the microarchitecture, is that?
Yes. So in order to give it really like the model formal semantics, you have to translate it to something. You need to elaborate and go through the process of changing that system Verilog into. And so it doesn't. There are some structure and so that what we need are some monotonicity and other things that system Verilog doesn't obey. And so what we do in that case, we need to, we are more conservative, so we replace with X's in places where they might not, and try to do proofs with that. So we never reason on system Verilog itself, but we have the connection to it. We know that which signal correspond to what expression, etc. Yeah.
I was curious about your design choice to start from system Verilog as sort of the source code, and not start at either higher or lower level like BlueSpec or Verilog.
Well, system Verilog is what our designers write. That's why we are starting. Yeah. Yeah, that's given. That wasn't our choice. Wouldn't be mine. Yeah.
What would have been?
A limited system Verilog.
Yeah, I guess just following up on the comment, you translate system Verilog to final state machines, and you say you wish limited system Verilog. So I was wondering, is there actually a coding standard that makes that extraction easier, or is it pretty much you get arbitrary, like the arbitrary system Verilog, and then you need to try to recover final state machines?
It's even worse because sometimes it's inherited pieces from other projects, and there weren't very. So it depends probably on the business unit and company. And like when I worked at Centaur, it was a small company, and everybody was doing whatever they want. So you couldn't limit them to anything, or you could, but if we had somebody like CEO that would do that, but he wouldn't. Everybody had freedom to use any part of the language they wanted the way they wanted. So bigger companies have a little stricter rules, but because they inherit sometimes some pieces of design that it tends to be pretty messy and not what you would want. And honestly, ideally, we could generate correct design for them if they would allow us, at least for parts of the design, but it's not how it works.
So then
You would have to change the culture of the...
Yeah. So then how do you extract from the system Verilog that you get? How does your extraction kind of like, do you extract all the final state machines or like 80%?
Well, we in this case, it's we take the, well, we actually take more than ALUs. We take the whole execution cluster and first translate that in this path that I showed before. So we take much bigger portion from hierarchy to netlist, and then we just look for the final state machine for ALU that I want to verify, and just build the model for that.
You do that manually?
No, not manually, automatically. No, that wouldn't work manually. It's too big, and it's also that even when I say something is written in system Verilog, it's only partially. There are a lot of macros that need to be translated and microcode parts to design. So actually the simulation people, they have to wait hours to do that. Yeah.
I know you can defer questions if you want to on the top. The top.
Oh yeah, yeah. Maybe I. Okay, thank you. So yeah, we were talking about that, and actually with this approach, with FGR, we can verify more than 90% instructions automatically without any intervention from us. We just need to set the interface for ARU, latency, and give all the information, write the spec, and it's done. But there are, of course, some instructions like square root, for instance, that we need decomposition, and people know also multipliers are notorious and very hard to verify. And we have dozens of opcodes that do different variation of multiplications, etc. And so, like in case of division or square root, we need to decompose it into iteration of the algorithm. Depends how it is implemented, and prove some invariant about it, and then compose it together. That's why it's really important that we can reason. For instance, the model checker nowadays are so good that you can probably verify the most of the instructions by model checking it, but because they are just simple. But once you get beyond that, you do not have a way to compose the results. So if you come across instructions that needs a little bit intervention, then you cannot deal with this model checking tools. So you need something stronger. And also, so you either decompose the specification and prove things step by step, or you decompose the input space and do the case splitting, or you have to decompose this design, but then you need to make sure that making this decomposition you didn't make some mistake, and so to prove that actually when you put it together that it behaves the same way as original design and things like that. So mentioning about multipliers, we have a fully verified and automatic tool that is also in public domain actually, and it works better than any tools I've seen, including these symbolic algebra tools that people write about. The reason is that it's kind of more versatile. It can use various booth radices, so different types of summation trees, and sometimes these algebra methods can verify only very clear design that has, let us say, a multiplication of n by n operands. And here you can have different sizes of operands. You can have saturation, you have different flags and force, etc. So we can go basically up to 1,000 by 1,000 bit multiplier in a few minutes. And so how does it do? It uses rewritings, or the rules are verified, and in case, the only thing what needs to be identified is half adders and full adders, what usually are implemented by macros, but sometimes, we can also identify them just sweeping through the network. We have different heuristics that find them. And if we don't find all of them, then we can always use at the end FGR, because the rewriting brings the specification and design close enough that it's just much faster. So just summary. So we specify and verify more than 3,000 opcodes, and our specification are connected to x86 specification. We use the automation built into ACR2 prover, and different automated procedures that our group built. And so we do need to re-verify it basically every day, and it is changed hundreds of times by different people. So we need this fast path to building model and rerunning proofs. The regressions run regularly, and then they create actually web-based documentation about to what extent each ARU was verified, which proofs are missing, and which proofs are there, but they failed for one reason or another. And as I mentioned, the debugging is supported by tools that are outside ACR2 and designers are familiar with. So unlike in the past, in this project, we were actually on the very front line of the verification. The reason was that it was a completely new project, and the simulators weren't ready actually for testing people. So many times we got a unit that was completely untested and had to deal with that. Okay. I just mentioned that, okay, we can skip that. We hope to expand further beyond what we have done and work also on out of order and micro code verification. Here are some publications that were done. Thank you.
Thanks, that was great. You went
Sorry.
from the high level to the low level, all in a very lucid presentation. Thanks for that. So let's see. Let's start with Ben, and then Satnam, and then Peter.
Can you talk a little more about the interaction with the actual hardware designers and what kind of value they see in that interaction?
We had very good experience actually. They were very happy. We had also a way for them whenever they fix bug, they could rerun proofs automatically, and they, yeah, I think were great supporters, and they were willing also change things when we asked them to make something nicer. And yeah, I think that we worked with designers that we didn't know, of course, because the group was new for us. And by the end of the project, they all wanted other things that we go and verify. And so, yeah, I couldn't be more happy. And I think they did see value. That was very clear.
Satnam.
Thanks for a great talk. So if I understand correctly, your approach involves synthesizing an FSM representation from RTL, which you've implemented yourself. Is that a formally verified transformation?
Yeah, so as I mentioned, there is several steps. And the very first step is not, because it cannot be, because system Verilog doesn't have formal semantics. But we were very careful into like translating into more conservative maybe things, and it has been used for years. So we have a reasonable, yeah. This first step is not validated. From then on, all the composition of function of each wire into basically next step function, and so that's verified. So the reason why we do flattening is also that sometimes you need to iterate 1,000 times in order to obtain this composition. And so that would be, ideally we would basically simulate this step each time, every cycle, but that would take just for long. That's why we composed these functions and verified that they were correctly composed. And yeah.
Thank you. Okay, we get a last question from Peter.
Let me read your lessons learned slide.
Yeah. Here. So, yeah, I can let you.
You can read it.
Yeah. Faster than I can.
Okay, so thanks, Ardana.
Thank you very much.